Hey there, welcome back. We're going to move along inside this unit on polynomials, and we're going to talk about polynomials that are functions. They're going to have only one variable. Our objectives are: how do I determine the degree and the leading coefficient of a polynomial function? How do I use synthetic division to evaluate a polynomial? We did this when we learned synthetic division. How do I describe end behavior? How do I determine if the poly is an even or an odd degree function? And then state the number of real roots or zeros from a graph. So all we can pick off of the graph is the number of real solutions. All right, so let's get started with this. Okay, a polynomial function. These are the characteristics. It's going to have only one independent variable. Okay. So all the same letter. I mean, you'll have f of x equals x squared plus 2x. F of x is equal to x cubed plus 2x squared plus x minus 7, right? We don't have any negative exponents, which also means that we don't have any variables in the denominator. To find the degree, look for the largest exponent. So in this example up here, this is a degree 3 because that's our largest exponent. Okay. The leading coefficient is the coefficient in front of the variable on the term with the highest exponent. So in this case, our leading coefficient, we call it a sub n, is equal to positive 1. And our polynomial is in standard form when it's in descending order. So it's going to go from the biggest exponent, will be the leftmost, and then it's going to go to the right in decreasing order. Right, so let's take a couple of these and just go through some of the characteristics. Determine if the expression is a polynomial. If it is, state the degree, the leading coefficient, and write it in standard form. All right, so number one, we don't have any negative exponents, and we aren't dividing by a variable, so we are a function. All right, and my degree, I scan for the highest exponent, so this is a degree 6. My leading coefficient, a sub n, is going to be 5. And then to write it in standard form, I have to go in decreasing order of my exponents. So 5x to the 6th minus 3x to the 4th plus 12x cubed minus 14. We don't have to worry about plugging in 0 values for missing terms, okay? All right, number 2, down here, number 2. We have 12x squared minus 3xy plus 8x. Notice that I have an x and a y, so this is not a poly function. Poly function, not. So I don't have to worry about answering any of the other questions, all right? Why don't you try 3 and 4 as your video questions and then come back and check your solutions. All right, number 3. This one is a polynomial, or a function. Actually, that's what we're trying to determine, is a polynomial function. My degree, again, is 6, because here's my largest exponent. My leading coefficient, called a sub n, is equal to negative 1. And then to write it in standard form, I do negative 1x to the 6th plus 8x to the 4th minus 2x cubed plus 3. Okay. On number 4, notice that I'm dividing by a variable. That means that I have a negative exponent, so this is not a function, a polynomial function. Let's go ahead and put the word poly in there because it is a function. It's going to be a rational function, so it's not a polynomial function. It's a different kind of function. All right, so when we're evaluating, we can use synthetic division. Super fun, super fast, okay? The thing to remember is if it's asking you to find the function at a value, we don't switch the sign like when we're using division by a factor, okay? We keep the sign the same. So 1 goes out in the front. I check for missing terms. I don't have any. Make sure I'm in descending order. I am. Put my coefficients in. Begin the process. So I bring down the 1. 1 times 1 is 1. 1 plus 3 is 4. 4 times 1 is 4. 4 plus 2 is 6. Here's my remainder. Okay, so f of 1 is equal to 6. And again, we know this from before that x minus 1 is not a factor, and 1 is not a solution or a root. Okay? So you try number 2 on your own. Come back and see if you got it right. All right? We're finding f of 3. We're using synthetic division to get there. So the 3, because it's already kind of been solved for, so 3 goes on the outside. And then I check to see if I have any missing terms. I don't. I'm in descending order, so I'm all good. So it's 1, 2, negative 4, 2. I bring down the 1. I multiply. I add. I multiply 5 times 3. Get 15. I add. I multiply 11 times 3. I get 33. I add. And that gives me 35. So my remainder is 35. So that means f of 3 is equal to 35. If I would plug that in to this equation, like I've done in the past, I would get the same value. It says that x minus 3 is not a factor. And it says that 3 is not a solution or a root. Okay? All right. The evaluating a function at a function, we kind of have to go back old school and do the plugging in, the substitute. So basically, if you're going to evaluate a function at another function or at using an expression, what you want to do is everywhere, what this is saying, and we talked about this when we were in just linear, but anywhere there is an x over here on this side of the equation, we're going to replace it with an a and then follow whatever operation it tells us to do. So if I do g of a, that means anywhere there's an x, I got to plug in an a. So I get a squared minus 5a plus 8. I look to see if I can simplify anything. I cannot. Can I combine anything? I cannot. So I'm done. This is g of a. It's just plugging in another expression into your function. All right. This one has a multiple step process. So this is finding 3 times g of 2a. So you first start by finding g of 2a. So g of 2a, everywhere there's an x in g of x, I'm going to replace it with 2a. So I get 2a squared minus 5 times 2a plus 8. So g of 2a equals 4a squared. See why we have to know our rules of exponents? Minus 10a plus 8. Now I have to do that final step, the 3. So I'm going to go 3 times g of 2a. I already know what g of 2a is. I'm just going to multiply everything by 3. So I get 12a squared minus 30a plus 24. That's 3 times g of 2a. Okay? Now on this one here, this one's a little bit different because we're plugging in a binomial. These are monomials that we plugged in, monomial that we plugged in, all right? So now we're going to plug in a binomial. So we have to be careful when we square that, okay? So what we're going to do is anywhere there's an x, we're going to put in, let me erase that. We're going to plug in a minus 2. So I have g of a minus 2 is equal to, there's an x, so I'm going to put in a minus 2, and notice I'm going to square it. Now minus 5, and there's an x, but I'm going to replace it with a minus 2. I don't square it because the problem doesn't call me to do that. And then plus 8. Now I'm going to expand this. So I'm going to get a squared minus 4a, I'm just foiling, plus 4 minus 5a plus 10 plus 8. Okay? So now I'm going to combine like things. I only have one a squared, so I still have a squared. Then I have negative 4a plus 5a, so, or I'm sorry, minus 5a, so that gives me negative 9a. Then I have 4 plus 10 is 14, plus 8 is plus 22. And there's my simplified version. The whole trick is wherever there is an x on the right-hand side, you're going to substitute whatever's between the parentheses. So here's what I plugged in, a minus 2. Okay. All right, describing end behavior. Okay, so end behavior is a way, is what's happening at the arrows. As the arrows keep going on in whatever direction they're going, how do we describe it? Okay, so there's a very standard way of describing end behavior, and it is like this. You use the word as, x, this means goes to, okay, as x goes to positive infinity. So as you go out towards positive infinity, f of x, the y value, is going to be going in some direction. In this case, it would be negative infinity. So remember that the arrow is interpreted as goes to, and so it's read as x goes to negative infinity, f of x goes to negative infinity. All right. So these things will change depending on which part of the graph you're referring to. So positive infinity describes a graph that points to the right or up. Negative infinity describes a graph that either points left and or down. All right, so this is going to be a little bit tight for me to get in here, but I want to do a couple of these with you, all right? So pay attention to the arrow. This arrow is pointing, it's pointing to the left, okay? And it's pointing up. The left is what you're going to use when you describe the x behavior. The up is what we're going to use to describe the f of x behavior. So as x goes on and on to the left, which is negative infinity, then f of x, the y value, is pointing on up to positive infinity. For this end over here, so you're going to have two for every graph, two statements for every graph. As x goes to, remember this is going off to the right, so that's a positive infinity. F of x is going down, which is negative infinity. Okay? That's the first one. Notice that these are pointing in the same direction, okay? So this one is going, I know it doesn't look like it, but this one is going left and up. This one is going right and up. So left says as x goes to negative infinity, f of x goes to positive infinity. Okay, this one is going right, so that's positive infinity and positive infinity. So as x goes to positive infinity, f of x goes to positive infinity. Okay, so I want you to try the bottom two on your own and then come back and see if you got it right. Okay, let's call this one A and let's call this one B. Okay, all right, so for this one, this is going left, and so left is negative infinity, up is positive infinity, right? So as x goes to negative infinity, f of x goes to positive infinity. This one is going right and down. So as x goes to positive infinity, f of x is going to negative infinity. Okay. For B, these are both pointing in the same direction. As this one goes left, this one goes down. So this is negative infinity, this is negative infinity. As this one goes to the right, positive infinity, this one is going to negative infinity. It'll help you if you label them like this. I'm going to see if I can get this to fit in here. As x goes to negative infinity, f of x goes to negative infinity. And then I'm going to have to go up here for the right-hand behavior. As x goes to positive infinity, f of x goes to negative infinity. Okay? All right, so the way you tell if a graph represents an even degree function or an odd degree function is by the arrows. If they point in the same direction, then it's an even degree function. It's going to be like a degree 2, a degree 4, a degree 6, okay? That'll be the highest degree exponent. If they go off in opposite directions, that means you have an odd degree function, okay? So they point, odd degrees, the arrows point in opposite directions. All right. When we talk about the real zeros, everybody plug in the word real because we're talking about real zeros right here. Real zeros, not the imaginary, not the ones with the eyes, okay? So that's where the graph touches or crosses the x-axis, okay? Just in future, touching is always going to count as 2 roots, okay? So if you have an even degree polynomial, you're going to have an even number of roots. The most you're going to have corresponds to the degree. The minimum that you can have is none, okay? For an odd degree polynomial, you're going to have an odd number of roots. The maximum you're going to have is that matches the degree, and the minimum is 1. These always have to cross at least once, odds do, because the ends go in opposite directions, so at some point it's going to have to cross. Whereas with an even, these ends go in the same direction, so you could have something like this where it never touches the x-axis. Okay? All right. So describe the end behavior, state if it's even or odd degree polynomial, and then the number of roots. You don't have to estimate the roots or anything. You just have to say how many there are. So my end behaviors, okay, I'm going to look here. This is going left and down. So as x goes to negative infinity, so this is going off to negative, f of x is going to negative infinity. This arrow is going to the right, that's positive infinity, and it's going down, that's negative infinity. So as x goes to positive infinity, f of x goes to negative infinity. The degree, both of them are pointing down, so this has to be an even because my ends go in the same direction. The number of zeros, if I look where it crosses the x-axis, it doesn't, so this one is none. It could cross, but in this case it doesn't, all right? Now we're going to look at this, ignore those green dots. I think that was from a previous illustration that I did, and I think we don't need those, all right? So my end behavior, as x goes to negative infinity, this one is going to negative infinity. So as x goes to negative infinity, f of x goes to negative infinity. And then for the other arrow, look here. This is going to the right, that's positive infinity, and it's going up, that's positive infinity. So as x goes to positive infinity, f of x goes to positive infinity, okay? My arrows are pointing in opposite directions, so my degree is an odd degree. Okay, I don't know exactly what it is, but I know it's odd. And then my number of zeros, count the number of times it crosses the x-axis. 1, 2, 3. 3 zeros. 3 real zeros. Plug in this. This is real. We're talking real zeros. We're not talking about imaginary, okay? So this would be find the number of real roots, okay? All right. So these are going to be what we're going to work on tomorrow in class. So thanks for listening, and I'll see you tomorrow.